Welcome. I'd like to present the paper Non Random Weight Initialization in Deep Convolutional Neural Networks Applied to Safety-Critical Artificial Intelligence. The running order is an introduction with motivation, novelty and background, the challenges of the convolutional layer, the proposed method, results and conclusion. The motivation is for safety-critical artificial intelligence in neural networks and to achieve repeatable determinism from learning session to learning session with no variations that are visible over regularization, as that is the form in the random states. The proposed form has the novelty that it will provide a higher performance. It achieves a repeatable determinism, so no variation from learning session to learning session. And there is a lower loss achieved earlier in learning, so there is less unlearning of the initial condition. The previous work was limited to perceptron layers presented at DeSE 19 in 2019 and achieved an almost equal score, showing the viability of a non-random scheme over a random scheme. This work was furthered in a journal version and embraced the Gloria-Xavier limits and achieved an equal score to the random forms. So the Gloria-Xavier and HE initializations, particularly because it's regarded as a state-of-the-art, are of interest to us, particularly from their weight, from their limit values. So in the previous work in perceptron layers, we can see some results here of the weights after learning, and in the random form we can see that the weights are diffused, but in the non-random form we can see that there are sharp correlations between the image pixels and the number of nodes. And this might have an advantage to rule extraction, as the generalization step may be easier as the sharp activations are in adjacent nodes and adjacent pixels. So deconvolutional layers would be different, and the previous form used in the perceptron layers wouldn't relate directly, and that's because perceptron layers had a fully connected nature, meaning that the order wouldn't be important, but the order that is in the convolutional layers may have an effect because of the restricted receptive field, and also there may be an effect of the weight order ramps in the direction of processing. The test case for this is the NIST dataset, and that relates to the previous work to make a comparison. And the first step to this is to calculate the sizes of the weights and the image size at every layer. That allows us to calculate the Gloria-Xavier limit values that we'll need for those layers to initialize the weights in a non-random form. And what we wanted to achieve in the proposed method was a form that would have more stripes and curves, as those are generally accepted as important to filters, and is also in tune with Hubel and Weasel and experiments with spider monkeys under light anesthetic. We also want to be able to provide a number of permutations for those initializations for each filter in the layer. And previous work that we had done in shuffle order in least adjacency might have a suitable benefit because it had an attractive quality. And that attractive quality to this application was that it could orientate vector values from horizontal to vertical over a number of iterations. And so from that point of view, it could reorientate our stripes and curves from horizontal to vertical. And we can see here in the diagram here that the black line, which is at the first iteration, has been reorientated to the vertical orientation in the red line at the penultimate iteration before the repeat occurs at vector length -1. So the form of this vector initialization with a non-random form is actually numerically fairly simple when viewed from an addressing point of view. If we take a value sequence, which will be determined in the next slide, and we take the addresses of those and address them through column, row, filter and depth in an order that's described in the paper. If we take the addresses and split them by 2 and take the second half of the vector, reverse it and place it into the first half vector's gaps, what we get is a resequencing of the addressing, which has a benefit of creating stripes and curves. And this is also iteratively applied and can provide a number of filter iterations for the layer. What you might notice is that the first value in the shuffle order is unchanged, so we alternate the vector before we apply the readdressing, and this doubles the number of filters. We did try some other experiments with offsets and resequencings, but they were less effective than this. So then what we found was the actual sequence that we're encoding into that with convolutional layers. Sinusoidal slopes seem to achieve the better values for convolutional layers, and linear ramps for the final perceptron layer. So we look at the filters that actually are being used. We can see the before learning and the after learning, and there is a difference between them to show what has been learned. We can see that there is dominance from the before learning to the after learning, but what we can also notice is on the non-random form that there are more stripes and curves, and the random forms are more speckled. But when we look at the differences between what has been learned when the random form and the before learning and after learning of both random forms and the non-random forms, there seems to be some comparison equality, but in actual fact the performance of the non-random form is actually better, and the reason for this is this form actually induces earlier learning. And what we can see here is that it's also robust to whether it is shuffled or non-shuffled, but in the non-random form we can see that the loss in learning has lowered earlier, and in the random form is about 2.0 at batch 100, and the non-random form is about 0.75 at batch 100. Therefore, it is using more of the data set more effectively earlier. So what we want to do then is, having proved that this can work with the Gloria-Xavier limits, is check the effect with HE initialization. What we didn't do was use HE initialization right from the outset, because the model had been optimized with Gloria-Xavier, and we would have to go through some rigorous optimization and to qualify the model with HE initialization from the start. So what we've done here is we have shown the benefits that HE provides over Gloria-Xavier and over each of the epochs. And what we can notice, even in the shuffled and the non-shuffled in the first epoch, that the best benefit is provided being the epoch that is after the initialization state. After that, the benefit is diminished and roughly equal, as the effect of the initialization has diminished in the subsequent epochs. So the benefit here is that we've achieved a higher accuracy, and we've achieved about 2.8% in the first epoch. Over the full 5 epochs, that diminishes down to about 0.52, but it's still worth having. But also what we've achieved here is that we have achieved this accuracy first time. There we haven't had to do a number of iterations with different variations of random forms in order to get the best value. And this is a value, and it's completely repeatable and deterministic, which is the value of dependable systems for safety critical AI. And it achieves the lower loss earlier, which might be able to use smaller data sets, but actually is actually using the data set more effectively right from the outset. And it is also robust to HE initialization too. Thank you very much. I should point out that the work has a couple of caveats, is that all the work here has been done with ReLU in terms of the HE and Gloria-Xavier, and we've only used black and white images in classification case. Thank you very much.